This meeting is being recorded.
Hi, everyone, and welcome to our weekly AATMN seminar. The speaker today is Corentin Lunel, and he's going to tell us about Hopf Arborescent links, minor theory, and decidability of the genus defect.
So, thank you very much for inviting me. So indeed, I will present results related to Hopf Arborescent links, minor theory, and decidability of the genus defect. And that was a joint work with Pierre de Hornoy and Arnaud de Mesme, which were my PhD advisors. And so I want to first tell you where we are going. So for now, nothing is defined. I just want that we have some kind of goal to reach, and most of the talk will be devoted to given context to these theorems. So what we do is that we introduce some mathematical objects, links and surfaces. Don't worry if you don't know what these are. Here are some examples. And we prove that there is some quantity related to the links that can be computed. And we prove that the surfaces can be ordered with a nice property that is called well-quasi-order. And so I will first talk about knot theory and explain more in detail theorem 1. Then I will talk about well-quasi-orders and explain more in detail theorem 2. And finally, I will give you outline of proofs for how we proved these theorems. So first, let me tell you about knot theory. So what is a knot? So a knot is an embedding of the circle into S3, so the ambient space. I choose S3, but you can think of it as R3 if you prefer. And we consider these knots up to ambient isotopy, which are continuous deformation without self-intersections. So if you want, you can, so I don't know if you can see, but you can see it as a rope, and you can distort this rope in space. You can bend it, curve it, extend it, as long as you don't cut it to glue it back later. And it stays the same knot during all of this continuous operation. So, for example, here is a figure-8 knot that I have here. It's also the figure-8 knot. And I can, using continuous operation, distort it into this representation here. So this is also a figure-8 knot because they can be related by an ambient isotopy. And on the left, this is the simplest knot that you can get, which is a standard circle, and that is called the unknot. And a link is a disjoint union of knots. So here is the simplest link you can get, which is two disjoint circles. And here is a more complex link, which is called the Hopf link. This is two circles that are interlaced. So from an algorithmic point of view, it's not clear how to input knots into a computer. So what we will do today is to restrict ourselves to tame knots, which are knots that can be put into broken lines in space. They can be represented by a finite number of segments in space. Like, for example, here is a figure-8 knot that is represented with segments in space, and that you can input into a computer. So this is a common assumption to restrict ourselves to knots admitting a polygonal embeddings. And that's what we will do today so that we can talk about algorithms on these knots. And they have another advantage. They admit knot diagrams. So a knot diagram is an unambiguous drawing of a knot. So whenever you have a tame knot, so which admit a polygonal embedding, even though here the knot is not polygonal, you can find some direction of projection so that you can draw it. And each point has at most 2 pre-images. And so you can sign each crossing and tell which strand is above the other one. So this representation are somehow equivalent. So I will just show you diagrams instead of this kind of rope thing, and this will be how I will draw knots today. And so what are natural questions about knot theory? So the first one that arises from the very definition is, are two given knots equivalent? So I am showing you two knots, and you can try and guess whether they are equivalent. So do there exist an ambient isotopy that transform this knot into this one? Which is not that simple. You can try to be more simple and set the second knot to be the end knot, like here, the circle. Like, is this knot equivalent to this one? It's not as easy, right? And from a topological point of view, you can also wonder what is the topology of the complement of a knot. Knots are very linked to the topology of their complement, so it makes sense to question ourselves about this. And these are hard questions. So for many reasons. The first one is that for us humans, it's hard to tell at first glance whether two knots are equivalent. So for example, with the question I have showed you, I just showed you, like this knot is not the end knot. It is a trefoil knot. So it is the simplest non-trivial knot you can get. How can you convince yourself? Here you can see that the strand overlap this one here, and the strand overlap this one here, and you can pull them apart, and you are left with some kind of twist here, and twist here that can be unmade, and then you have some knot here that is the trefoil knot. And this is different from the circle. And here, if you are very good at picturing things, you can see that this knot is the end knot, but it's hard. In fact, this is a Goritz knot, and it is known as being some kind of hard to prove it is an unknot. So these questions are hard for humans because it's complex. It's also hard from a theoretical point of view. It's not easy to provide an ambient isotopy that relate two knots. And so we could ask a computer to help us, but it's not that simple. We have some algorithm to answer these two questions, like the trivial knot recognition. We know it is in NP and co-NP from the work of Haas, Lagarias, Pippenger, and Lakenby for the co-NP part, but we don't know a polynomial time algorithm solving this question. Although a quasi-polynomial time algorithm has been announced by Lakenby some years ago. For the general question, are two given knots equivalent? We have an algorithm solving this question, but the complexity is incredibly high. It's a tower of exponential, and it's called elementary recursive. So it's also hard for a computer to answer these questions. So what can we do? It's hard to certify that two knots are the same. However, it's more feasible to distinguish two different knots. To do that, we use knot invariants, which are quantity defined for all knots that remain the same for all equivalent knots. So there are many of them. Here are some examples. There are very simple ones like tricolorability, which is the ability to color a graph using free color and ensuring some property on crossings. There are plenty of knot polynomials like Jones polynomial, Alexander polynomial, Conway polynomial, Amfly polynomial. There are homology associated to knot like Kovanov homology, Fleur homology, and there can be also complex objects like manifolds. Like when you have a knot, you can take a regular neighborhood and remove it of S3 to get a free manifold with boundary. And in fact, this is a characteristic of the knot. The Gordon-Luker theorem tells you that two knots are equivalent if and only if the free manifolds associated are equivalent. So from a computational point of view, it raises a lot of questions. How hard is it to compute this invariant, and how hard is it to compare them? Like, for example, it's not that simple to compare free manifolds. Then today we will focus on one such invariant called Seifert surfaces. So when you have a knot, you can be interested in the orientable surfaces embedded in S3 that admit the knot as a boundary. So, for example, here you have the unknot, and it can be obtained as a boundary of a torus with one boundary component, or it can be obtained as a boundary of a disk. Here is a trefoil knot, and it can be obtained as a boundary of this surface, which is in fact a torus with one boundary component, because indeed this surface has genus 1 and one boundary component. And then the genus of a knot is a minimal genus among its Seifert surfaces. So the genus of the knot is 0, because it can be obtained as a boundary of a disk, and you cannot go lower than 0. And the genus of the trefoil knot is 1, because it can be obtained as a boundary of a torus with one boundary component, but cannot be obtained as a boundary of a disk, because only the knot can be obtained as a boundary of a disk. And from an algorithmic point of view, we know it's decidable to prove that a knot has genus atmos k. We know this is in NP and co-NP, but we don't know a polynomial time algorithm. And now we can come to the space of what we do. We want to allow the surfaces, the Seifert surfaces, to be pushed into the 4-dimensional space. So what I mean is that you can see S3 as a boundary of the 4-dimensional ball before. And then you can look at orientable surfaces whose interior is embedded into before, and whose boundary is the knot that lives into S3. So it's quite complex to picture. And here I want to show you one example to help understand things. So here is a knot, and you can see that this knot can be obtained as a boundary of a disk that self-intersects 2 times on this kind of pattern, which is called a ribbon intersection. And these intersections can be pushed into before, and so that they disappear. So what I'm telling you is that this knot can be obtained as a boundary of a properly embedded disk into before. And so the 4 genus of a knot, which is the minimal genus of such a surface, orientable whose interior is into before, can be obtained as a boundary of a disk. So this knot has 4 genus 0. And
Corentin, can I ask a question there?
Yeah, sure.
All right, so the surface is in the 4 ball, right?
Yeah.
But the 4 ball sort of includes into the 5 ball and the 6 ball and the 7 ball. If I allow my surface to live in those higher dimensional spaces, is the genus probably unchanged?
Okay. Short answer is I don't know, because in 4-dimensional space you already have a lot of space to undo things.
Yeah.
So my gut feeling would be that going from 4 to 5 may change things, and that it does not change after 5.
Gotcha.
Because in dimension 4, what is noted are surfaces. You know, in dimension 4, like if you put a knot into R4, it is equivalent to the unknot, because you have enough space to move the strand around and make every crossing disappear. So what can be noted are somehow surfaces. And so I would say 1 dimension higher, you would have enough space to make everything disappear, and it should become trivial at dimension 5, but I'm not sure.
Thanks so much.
Yeah. So coming back to computational point of view here is, so topology in 4 dimensions is hell. We don't have a systematic framework to tackle a question, and we have a lot of undecidability results. Like, for example, we know that it is undecidable to compare 2 form manifolds. Also, last week, some results have been put onto archive. So we can compare 2 form manifolds if they are simply connected. But for general case, we know that it is undecidable. And so it is not a surprise that in dimension 4, we don't know an algorithm to decide if a knot has 4 genus atmos k. However, a natural variant on link from the Mesmer, Rick, Sedgwick, and Tonzer showed that it is NP hard. And now I want to tackle some detail about surfaces in dimension 4, which are a bit complicated, but the conclusion of this slide is quite simple. So every knot can be obtained as boundary of a disk whose interior is into B4. This is obtained by a coning construction. Like if you take a circle or a knot, more generally, you take a point in the interior on B4, and then you take all the lines between this point and your knot. So here you have a cone. And if you are a more complex knot, like the trefoil knot, you take a point, you take all the line. If you see it into S3, you will have a lot of self-intersections. But when you see it in B4, all the self-intersections disappear. And so you obtain the knot as a boundary of a disk. However, around this point here, which is called the apex, if you take a disk around this point and look at the boundary of this disk, it will be the same as the initial knot, because the knot only tapers to this point. And so what I'm telling you is that there is no way that around this point you find an homeomorphism between the disk and the standard R2 put into B4. So this surface would not be locally flat when the initial knot is not the end knot. And so it makes sense in dimension 4 to put some restriction on the regularity of surfaces that you consider. There are two kinds of regularity that you want to enforce. The first one is smooth, so you want your surface to be smooth. And more generally, you can just ensure that the surface is locally flat, which is what I was telling you about right now. And so dimension 4, these two classes are different. In S3, in dimension 3, that is not the case. Smooth is the same as locally flat, but above it's not the same. So what I wanted to say is that there is two categories of surfaces that give rise to two notions of four genus, the topological four genus and the topological four genus. And I was telling you that the conclusion of this slide is simple because our results are valid in both classes. So I will write G4 for either the topological one or the smooth one, and you can think of whatever you prefer, it is still valid. And to illustrate how hard these problems are, I want to take the example of the Conway knot. So this is a Conway knot. It has only 11 crossings, and it was proposed by Conway more than 55 years ago. And we know that it has been shown early that its topological for genus is 0. However, the question of its smooth for genus has been open until 2020, when Piccirillo showed, using some knot invariant, that the for genus is non-zero. And it was really a breakthrough. So for genus, quite complex. Another technicality that will be swept under the rug during the remaining of the talk is that when you consider Seifert surfaces with link, you want them to the link to be oriented. So you orient the link, and you want that the orientation of the Seifert surface match the one on the boundary, like that it's consistent. It's a bit worth mentioning because when you put different orientation on the same unoriented link, you can get different set of Seifert surfaces. Like, for example, here is a link with two knots components, and according to the orientation, I am showing you two minimal genus Seifert surface. So here it's a torus with two boundary components, which is a minimal Seifert surface for this oriented links, and it has genus 1. But here I'm showing you a bond, an annulus that is twist 4 times, and so the three shape here are above the big one here. And so it is a ribbon, so it has genus 0. So what I'm telling you is that Seifert surfaces depend on the orientation, and so it makes sense to consider orientation on links. And we orient the link afterward, although I will not picture the arrow on the drawings. And now that we have all the context, let's present again our theorem 1. So we introduced a class of links that is called Hopf Arborescent links, and we are interested in their genus defect, which is the difference between the classical genus and the for genus. And so because there are two notions of for genus, there are two notions of defect, but our theorem is valid in both categories. And our theorem tells you that for any integer k, there exists an algorithm deciding whether a Hopf arborescent link has genus defect at most k, which is significant in this area where we don't know how to do things in dimension 4 and where we have a lot of undecidability results. It's nice to have a decidable one. And now let's move on to well-quasi-orders. So to talk about well-quasi-order, I want to talk about our inspiration on the method that we use here, which comes from structural graph theory. So I will digress a bit about graph theory. A graph consists in two pieces of information, a set of vertices and a set of links between them that we call edges. So here are some graphs. The vertices are in red and the links are in gray. Oh, sorry. What happened? Okay. And structural graph theory investigates classes of graph. So, for example, the graph here has no cycle, and it is connected, and so it is a tree. And for example, structural graph theory can be interested into the class of trees. On graphs, we have some kind of operation and a relation, that is called the graph minor relation. And a graph H is said to be a graph minor of a graph J if H can be obtained from G, by a sequence of vertex deletion, edge deletion, and edge contraction. So a vertex deletion is just removing a vertex and the incident edges. And edge deletion is just removing an edge. And an edge contraction consists in merging the endpoints in that way. So let me show you an example. Here, this triangle is a graph minor of this graph. And we can show it by, for example, deleting this vertex and contracting this edge, which would yield this triangle. Or you could, for example, delete both these vertices and also obtain this graph. And this relation is interesting. Let's use it to study a class of graph that is called planar graph. So here is a map of France, a piece of map of France, and you can see that there is an underlying graph where vertices are cities and branching of roads, and links are the roads. And this graph is drawn into the plane, like you don't have two roads that cross. And not all graphs satisfy this property. Some graphs are not planar. They cannot be drawn on the plane. Like, for example, this graph, which is a complete graph on 5 elements called K5, cannot be drawn in the plane. And this is the same for this graph, which is called K33. So bipartite and complete of 2 times 3 vertices. And there is a nice theorem called Wagner's theorem that tells you that when you have a graph, G is planar if and only if it does not admit K5 or K33 as a graph minor. And so it's if and only if. And it's a powerful theorem because it relates topological properties on graph with substructures on graph. And in fact, Robertson and Seymour proved during a long series of 23 papers that they developed during 20 years and released all at once, that whenever you have a property that is stable for graph minor relation, so what I mean by that is if you have a graph G that satisfies the property is stable if every minor of G satisfies also the property P. So whenever you have a property stable for graph minor, then the property is characterized by a finite set of forbidden graph minors. So, for example, when P is the property being embeddable on a plane, the set of forbidden minor is K5 or K33. So, what is linked with well-quasi-order? In fact, they do not present this theorem that way. The way the theorem is the graph minor relation is a well-quasi-orders on graph. And so this theorem implies that every property is characterized by a finite set of forbidden graph minors. So the property could be being embeddable on a torus, on a projective plane, on a sphere, on more complex surfaces, or could be different kind of property, non-topological one. But still, just because the graph minor relation is a well-quasi-order, we have the powerful result that it's characterized by a finite number of elements. And now I want to tell you why this is the case. So now I will present well-quasi-order, and everything I say, you can think about it in the graph setting I was just presenting before. So an order is a well-quasi-order on X if whenever you get an infinite sequence of elements of X, you have an increasing pair in the sequence. So an increasing pair is an element xi that is in relation with an element xj that appear later. And as a simple consequence, if your set is well-quasi-order, you cannot contain an infinite antichain because it would be in direct contradiction with the definition. So how can we use it? Let's now consider a property that is stable on X for our well-quasi-order. It is stable if whenever X satisfies P, every element in relation with X also satisfies P. So now we have X that is well-quasi-order, the set of elements satisfying P, and we can look at the complement. And the complement will have some family of minimal elements. But because they are minimal, they are not in relation with each other. And because the set is well-quasi-order, you know that the family of minimal elements is finite. And because the property is stable, belonging to the complement of this set is equivalent to having none of these minimal elements as minor. Is equivalent to not being in relation with any of these minimal elements. And that's how you prove that whenever you have set X well-quasi-order, every property stable for your relation is characterized by a finite set of minimal elements. So this is a nice property that has strong algorithmic consequence. Because indeed, whenever your well-quasi-order is decidable, then you have an algorithm to test your property P. Because you only have to run the test for each minimal element. But so something that is great here is that you don't have to actually provide the minimal set of elements to prove that the algorithm exists. You just know that the algorithm exists because the family of minimal elements exists. And you just have to run the algorithm on each of them. And that's how we prove our theorem. Well-quasi-orders also have a consequence for people that are interested into order theory. I know you can derive some things from well-quasi-orders, but I'm not expert here. I'm more interested into the algorithmic consequences. And so now that we have the theorem 2 now that we have the well-quasi-order defined, we can come back to theorem 2. And so we have our class of link that is called Hopf Arborescent links. The minimal genus Seifert surfaces that are associated to them and that are called Hopf Arborescent surfaces. And we proved that this class of surfaces is well-quasi-ordered by a surface minor relation that is called, a surface containment relation that is called surface minor. And this kind of result is in line with other results about surfaces associated to links. However, we kind of remove some assumption about the shape that the other surface can have. Like they only use positive crossing, and we use both positive and negative crossing. And we enforce tree structures, and usually they don't. So just to say that this theorem is can be put in relation with other kind of well-quasi-order on surfaces associated to links. But now let's move on to the outline of proofs. And first, I need to define properly what is this particular family of links that I consider. So to define these links, we use Hopf links as building blocks and some operation on them. So remember Hopf links, which are this link, so two circles that are interlaced this way. And a Hopf band is an annulus whose boundary is this link. And according to the sign of the link, you can get both positive Hopf bands and negative Hopf bands. And now we define an operation called plumbing, which merges some part of a surface with a Hopf band in this way. And by defining precisely what plumbings mean, we are able to associate to each labeled plane tree, oriented plane tree, a surface. And we call the family of surface that we obtain this way the Hopf Arborescent surfaces. And so the labels correspond to the sign of the Hopf band, and the orientation is relevant for the operation of plumbing that we define. And then the Hopf Arborescent links are the links that we can obtain as boundary of the Hopf Arborescent surfaces. So by definition, to each Hopf Arborescent surface and to each Hopf Arborescent link correspond at least one plane tree. And so we have three families of objects. We have plane trees, we have surfaces, we have links, and on each of these objects, we will define a minor relation. And then to prove our theorem, we will exploit the connections that appear between this minor relation. So the first one on tree is quite standard. So we'll call this relation the tree minor relation. And we will say that a tree T1 is a tree minor of T2 if T1 can be obtained by contracting paths to edges and deleting leaves. So it's quite similar to graph minor, but here we do not allow an edge to be contracted to a single vertex. We require a path to be contracted to at most an edge, so it changes things. But here's the example. So you have this tree, and it can be obtained from this one by deleting two leaves and contracting one path to an edge. So that the endpoints, the labels of the endpoints are still the same. We also have a surface minor relation on surfaces, which was introduced by Bader. And we say that a surface sigma 1 is a surface minor of sigma 2 if sigma 1 is isotopic to a subsurface of sigma 2. So here, this Hopf band can be obtained as a boundary of a small neighborhood. Sorry, this Hopf band can be obtained as a boundary, as a neighborhood of this orange curve here. So what it tells you is that this Hopf band is a surface minor of this surface, which is a Seifert surface of a trefoil knot. And equivalently, to obtain surface minor, you can cut along arcs. So for example, if you cut this surface here, so you would obtain a surface that is isotopic to the Hopf band and get back the results that this Hopf band is a surface minor of this one. And then the link minor relation that we define is that a link L1 is a link minor of L2, so when L1 and L2 are Hopf arborescent links, if L1 can be obtained from a tree T1, if L2 can be obtained from a tree T2, and T1 is a tree minor of T2. That's our relation. And now let's detail the approach we use. So for theorem 2, it's how do we prove the theorem? So that the class of Hopf arborescent surfaces is well quasi-ordered by surface minor. We exploit the Kruskal tree theorem on trees. So the Kruskal tree theorem states that labeled plane trees are well quasi-ordered under the tree minor relation. So how do we do? We prove that if T1 is a tree minor of T2, then the surface associated to T1 is a surface minor of T2. And then it's enough, because if I give you an infinite family of Hopf arborescent surface, you can just pick one tree associated to each surface, and it gives you a sequence of tree. We apply the Kruskal tree theorem on this sequence, and it tells you that T1 is a tree minor of T2. It's great, because then this property tells you that the surface associated to T1 is a surface minor of the surface associated to T2, and we have proved that the surface minor relation is indeed a well quasi-order on our family of surfaces. So how do we prove this property here? So T1 is a tree minor of T2 if we can delete leaves of T2 and contract paths of T2 to edges. So it's easy to see that deleting a leaf yields a surface that is a surface minor after the deletion. So here H is some Hopf that corresponds to a leaf, and we can just cut along this arc and isotope this disk here back into the surface, and we get our surface minor. So it's quite easy to see for leaf deletion. For path contraction, it's a bit more complicated. So there is work to do here with orientation. So this slide is complex, but the point of this slide is that we define precisely plumbing, and we put a rule on orientation on the Hopf band so that everything works. So here is a rule. Let's not take too much time understanding it. I just want to say that there is some work about the definition to make the definition work, and some work around orientation on the Hopf bands. And so how does the proof work for contracting path to an edge? What we do, so again, the pictures are a bit complex, but the point is that if you want to prove that this path can be contracted to this one, and that this behaves nicely with respect to the surfaces associated to the tree, we prove that we can realize this edge contraction in trees by a cut in the surfaces. So here, on this example, we want to prove that we can contract this path to this one. And so what we do is we cut along this curve here, in this way here. And then we have to check that the construction still yield the proper surface after the cut. And to do so, we have to check the orientation, and that things still work. And that's what we do. Essentially, we prove for each possible path of size 3, which is enough to prove it for arbitrarily large path, that we can realize this by cutting. And doing so, we show that if T1 is a tree minor of T2, then the surfaces associated are surfaces minor. And that is enough to prove our theorem 2. Now let's move on to theorem 1. So recall, for any fixed k, we show that there exists an algorithm deciding whether a Hopf arborescent link has genus defect at most k, where the genus defect is the difference between the classical genus and the forward genus. And so we leverage the well quasi-order theory, like the property I have shown you before. So what you have to do is that you have to get a property that is stable for your minor relation. You have to get that your minor relation is decidable. and that your minor relation is a well-quasi-order. That's what we do. First thing, we show that the defect is monotone with respect to link minor. And to do so, we use something that was already noticed by Bader, Feller, Leeuwark, and Lirty. And that is the fact that the defect is monotone for surface minor. And then, because of the definition, it's the same for link minor. Then we use a proof very similar, in fact, the same proof as what I just showed you for theorem 2. We just have to consider the boundary in addition to prove that Hopf Arborescent links are well quasi-ordered by link minor. So you take your link, you take the trees associated to them, you look at the surfaces, you cut, and then you notice that the surface you obtain after cutting still gives you the original link, and that's all. And then we show that the link minor relation is decidable. And let me come back to the first point. If the defect is monotone with respect to link minor, it means that having defect less than k is a stable property for the link minor relation. And so we can apply the well-quasi-order machinery to prove theorem 1, that there exists an algorithm, and the algorithm is check for every minimal element of the complement. So to show that the defect is monotone, it is okay. Let's not take too much time on it. The proof uses a cut and paste construction. So you take a surface, you take another one, we cut things, and everything works around with minors. Something worth to note, though, is that our surfaces have a properties. They are what we call fibered, and it tells you that they are of minimal genus, and it is useful for this proof. And that's all I want to say about this part. And about the decidability, how does it work? Because it's not that self-evident, but because our objects are linked to trees, we can exploit these trees, and in fact, we brute force on the level of trees. So how to test the link minor relation between two links? So I have two links. What we do is that we enumerate all possible trees that yield the first link. How to do so? Like we just construct the surface associated to the tree, and take the boundary, and then use standard knot theory algorithm, like standard the knot theory algorithm deciding whether the two knots are the same, to tell you, okay, this tree indeed gives you this link. And because the number of vertices used to get a link is bounded by the link, you know that this process stops. Same thing for the second tree. For the second link, sorry. So we have two families of trees, and then we brute force all possible tree minor relation between these two sets. And if two trees are minor one of each other, then you know that your link are minor one of each other. And that's how we show decidability, which is enough to prove our theorem 1. So now some perspective. As I told you, the surface we use are fibered, and we wonder if the surface minor relation could be a well quasi-order on fibered surfaces, because we used a lot that property, and so proving this would need to relieve the arborescent part. And it's not that simple, but it's still a nice question. And also, as I was telling you, the algorithm we provide is not explicit, and we wonder if we can find an explicit one. And also prove something in general case and more broad family of links. So thank you for listening, and do you have any questions?
Thank you. Maybe before we get to questions, I would ask everyone to unmute themselves and give a round of applause for our speaker today. And now feel free to ask questions.
I would have one. Namely, if I understood you correctly, your theorem 1 says that there exists an algorithm that says whether the genus defect is less than k. But if I would now ask you to give me an algorithm that does this, that would not be easy, right? Like, did you also do research in the direction of coming up with an actual algorithm? Because that would mean you would have to find those minimal elements, right?
So absolutely, indeed, that is very difficult to provide the set of minimal elements. And also, I told you that the theorem is valid in both categories. So depending on the class of regularity you enforce on surface, you will come up with different set of minors for the two classes. And so I'm wondering about a constructive algorithm, but it would be very hard to find indeed the minor. So it is it's more a result about what is feasible, and we know that one algorithm exists at least.
Yeah, that's super interesting. Thank you. In general, it was a very interesting talk.
Thank you.
Dave, go ahead.
Did you want me to go, Sarah?
Yes, please.
Thank you. I haven't thought about knot theory in a while, so this was a very enjoyable talk. I have a question about the generalization. So a Hopf link is a two-braid, which is, say, the generator is sigma, it's sigma squared. So could you extend this to two braids where you have an even number of twists rather than two?
So short answer is what we do cannot be extended simply to an arbitrary number of twisting, even if they are even, because we know that the family of annulus with just 2n twist, and you take n an integer, is an anti-chain for the surface minor relation. So there is no hope to just drop this assumption of just two twists and apply exactly what we do. Like other method could prove that it is decidable, but not our well-quasi-order machinery.
Okay, good. Thank you.
Good question.
I had two questions, if I may. So the first question, is it pretty easy to see that there are an infinite number of Hopf arborescent links?
Sorry. The question, is there an infinite family?
Is it easy to see that there's an infinite number of them? Non-equivalent.
Yes. How to do so? Okay. Okay, I have something. So this knot here that I presented you is obtained with this pattern. And we showed also that if you take a tree and you have some patterns that are distant of at least one edge, then the defect of each pattern is additive. And so if you take very large tree and you repeat this pattern, you will obtain a link whose defect is at least the sum of the link of each pattern. And that will show you that you will get different nodes because their defect will be different, and you can go arbitrarily large. So that's a way to construct very high like links with very high defect, and also different links.
Nice. Yeah, I like that explanation, because you propose this class on which you have decidable algorithms, but then you're sort of using that algorithm to prove this classes. So the other question I had was sort of a follow-up on Teresa's question. You prove that these algorithms exist, but without knowing the minors, we don't have the explicit constructive algorithm. So yep. I'm going to use the word decidable, even though I don't really know exactly what it means. Is it known that it's decidable to sort of find the finite set of minors?
It seems to me that I have seen that it is not in the context of graph, I believe. It seems to me. So I'm very not sure of the answer, but the real answer is that it's usually very hard, at least, to find them, and for sure I don't know an algorithm doing so.
Right.
And I would also say that both for graph theory and for what we do, like that is where the topological property or geometrical property of your object come into play. Because the algorithm otherwise are very combinatorial. Like you have graph and you check minors, and we have not, and we check minors on trees, which are very combinatorial. And so it's kind of strange that this combinatorial algorithm can cover so much geometrical and topological properties. And the reason for that is that the topological work and topological geometrical properties were put into finding the actual minors. And yeah, that's what I wanted to say. I don't know of an algorithm finding minors.
Sure. Thanks so much. Very interesting talk.
Thank you.
Do we have further questions for Corentin? Okay, so in that case, I'm going to stop the recording here. Thank you very much, Corentin, and then whoever has questions can add them offline.
So thank you again.
Thank you.